Welcome to this model. In this presentation, let us have an insight of antenna noise temperature and GBT. There is a continuous background of noise like electromagnetic radiations in the atmosphere. These radiations arrive from outer space and are termed as cosmic noise. In general, cosmic noise decreases with the increase in frequency and is of considerable importance in VHF and lower UHF bands. Its magnetic property depends on the segment of celestial sphere in which it is observed. So its intensity is maximum towards the center of our own galaxy and minimum when observed along the pole about which the galaxy revolves. The brightness temperature of an extended source of radiation measured in a particular direction is the temperature of the black body, which yields brightness equal to that of the source under consideration. The brightness B defined as the power received per unit area of aperture per cycle of bandwidth per unit solid angle and at radio and data frequencies is related to the brightness temperature TB by the Rayleigh-Jeans formula, that is B is equal to 2 kTb divided by lambda square, where K is the Boltzmann constant and lambda is the wavelength. The brightness temperature specifies the intensity of the electric field in a given direction at a given frequency. The measurable temperature is then the mean brightness temperature in the field of the antenna pattern and is called antenna temperature. The antenna absorbs the cosmic noise at one temperature and an intervening absorbing atmospheric noise at another. The combined temperature of the cosmic noise and atmospheric noise is called the space temperature, the brightness temperature or the antenna temperature of an ideal antenna. The amount of noise which enters the antenna depends on the entire radiation pattern, including the side lobes and types of objects they illuminate. Land is almost a complete absorber, hence those portions of the radiation pattern which illuminate the ground absorb a noise source at the ambient temperature. A perfectly reflecting surface such as the sea or a road appears very cold if it is oriented to reflect radiations from the sky to the antenna. The choice of polarization also influences the amount of sea and land absorption. So the noise power per unit bandwidth available at the terminals of a resistor or at a temperature Tr can be written as P is equal to K into Tr. So if the receiving antenna has dissipative loss so that the radiation efficiency eta radians is less than unity, the power available at the terminals of the antenna is reduced by the factor eta radians from that intercepted by the antenna. Radiation efficiency is defined as the ratio of the output to input power. This reduction applies to received noise power as well as received signal power, so as the noise temperature of the antenna will be reduced from the brightness temperature given by the factor eta radiant. In addition, thermal noise will be generated internally by resistive losses in the antenna, and this will increase the noise temperature of the antenna. In terms of the noise power, a lossy antenna can be modeled as a lossless antenna and an attenuator having power loss factor of L is equal to 1 by eta radians. So the resulting noise temperature seen at the antenna terminals can be given as Ta is equal to Tb by L plus L minus 1 by L into Tp. So this can be written as eta radians into Tb plus 1 minus eta radian into Tp. Ta is the antenna noise temperature. It is a combination of the external brightness temperature seen by the antenna and the thermal noise generated by the antenna. A matched load at this temperature will produce the same available noise power as does the antenna. This temperature is referenced at the output terminals of the antenna, and Ta is equal to Tb for a lossless antenna with eta radians is equal to 1. So if the radiation frequency efficiency is 0, meaning that the antenna appears as a matched load and doesn't see any external background noise, then it reduces to Ta is equal to Tp due to thermal noise generated by the losses. If the antenna is pointed toward a known background temperature different than T0, then it can be used to determine its radiation efficiency. And if in the Nyquist relation that P is equal to K into TR, if the resistor R is replaced by a lossless antenna of radiation resistance R in an anechoic chamber at temperature Tc, and the noise power per unit bandwidth available at the antenna terminal is same as provided by Tc is equal to Tr. So now if the antenna is removed from the anechoic chamber and pointed at a sky of temperature Ts, the noise power per unit bandwidth is again same. And we can say that the antenna has a noise temperature equal to, that is Ta equal to sky temperature Ts. Using an antenna to measure the distant temperature in this way is a possible remote sensing, and the antenna in this application may be called as a radio telescope. This passive mode sensing is in contrast to the active remote sensing of the channel. To measure the distant or sky temperature, the antenna noise temperature may be compared with the resistor at an adjustable temperature Tr by an alternative connecting antenna and a resistor to a receiver. And the receiver detects no difference, then Ta is equal to Ts, that is equal to Tr. The noise temperature of an antenna is equal to the sky temperature and not the physical temperature of the antenna. This contrasts to the resistor, which is completely lossy and therefore has a noise temperature equal to physical temperature. Thus, for a radio telescope antenna, the noise power per unit bandwidth is given by P is equal to K into Ta, where Ta is the antenna antenna noise temperature of the antenna's radiation resistance determined by the sky temperature at which the antenna beam is detected. And hence a radio telescopic antenna may be regarded as a radiometer for remote sensing the temperature of distant regions coupled to the system through the radiation resistance of the antenna. An extreme view is to imagine that with a radio telescope we can in effect stretch the wires from the terminals until the resistor R comes into contact with the distant region. So we have assumed that here the antenna has no thermal losses and also that all of its pattern is encompassed by the region being observed. So multiplying by bandwidth we obtain the total power available as P is equal to KTAB, where B is the receiver bandwidth. It is often convenient to express the received power per unit bandwidth in terms of flux density. Thus, dividing the effective aperture of the antenna, S will be given by P divided by AE, that is KTA by AE. So here we have assumed a single celestial source whose extent is greater than the antenna beam. So in practice, the antenna temperature may include contribution from several sources. So under observations, it may be so the source may be superimposed on a background temperature of a temperature region. To measure the temperature of a source under these circumstances, the radio telescope beam is moved onto and then of the source, and the incremental difference temperature delta Ta can be measured. We can now analyze the noise characteristics of a complete antenna transmission line receiver front end. Okay, this system is shown in this figure. In this system, the total noise power at the output of the receiver N0 will be due to the contributions from the antenna pattern, the loss in the antenna, the loss in the transmission line, and the receiver components. This noise power will determine the minimum detectable signal level for the receiver, and for a given transmitter part, the maximum range of the communication link. So the receiver components shown in this figure consist of an RF amplifier with a gain of GRF and noise temperature TRF, a mixer with an RF IF conversion loss factor LM and a noise temperature TM, and an RF IF amplifier with a gain GIF and noise temperature TIF. The noise effects of later stages can usually be ignored since the overall noise figure is dominated by the characteristics of first few stages. The component noise temperature can be related to noise figure as T is equal to F minus 1 into T0, and from this the equivalent noise temperature of the receiver can be written as TREC is equal to TRF plus TM by GRF plus TIF LM divided by GRF. The transmission line connecting the antenna to the receiver has a loss LT and is at a physical temperature TP. So from this equation, its equivalent noise temperature TTL is equal to LT minus 1 into TP. Again, we find the noise temperature of the transmission line and receiver REC cascade is TL plus TREC is equal to TTL in plus LT into RTREC. That can be written as LT minus 1 into TP plus LT into TREC. The noise temperature is defined at the antenna terminals. So the entire antenna pattern can collect noise power. So if the antenna has a reasonably high gain with relatively low side lobes, we can assume that all noise power comes via the main beam, so that the noise temperature of the antenna can be written as TA is equal to eta radian plus into TB plus 1 minus eta radian into TP, where eta radians is the efficiency of the antenna, TP is its physical temperature, and TB is its equivalent brightness temperature of the background seen by the main beam. One must be careful with the approximation, as it is quite possible for the noise power collected by the side lobes to exceed the noise power collected by the main beam if these side lobes are aimed at a hot background. So the noise power at the antenna terminals, which is also the noise power delivered to the transmission line, is NI is equal to kBTA. That is equal to kb into eta radians into TB plus 1 minus eta radians into TB, where beta is the system bandwidth. And if SI is the receive power at antenna terminals, then the input SNR at the antenna terminals is SI by NI, and the output signal power is given by S0 is equal to SI into GRF GIF divided by LT into LM. That is equal to SI into G system. G has been defined as a system power gain. The output noise power N0 is given by NA plus KB into TTL plus REC into G system. That is equal to KB into TA plus TTL plus TREC into G system. So when you take KB outside, KB into eta radians into TB plus 1 minus eta radiant into TP plus LT minus 1 into TP plus LT into TREC into GSys. So this can be written as KB into TSys by into GSys. So the TSys has been defined as the overall system noise temperature, and the output SNR is given by S0 by N0 is equal to SI by KB into TSys, that is equal to SI divided by KB into eta radian into TB plus 1 minus eta radian into TP plus LT minus 1 into TP plus LT into REC. So it may be possible to improve the SNR by various signal processing techniques, and it may appear to be convenient to use an overall system noise figure to calculate the degradation in SNR from input to output for the above system, but one must be very careful with such an approach, because noise figure is defined only for N is equal to KT0 into B, which is not the case here. It is often less confusing to work directly with noise temperature and pass as we did above. Thank you.